So let's now think a little bit about how these waves evolve. So we know how they're generated, we know about their propagation properties, but imagine we have a big wind event that generates a whole bunch of waves with a whole spectrum of frequencies. How do these waves subsequently evolve over time? So this initial wind generation event with all these waves, we would call usually a wind sea, or sometimes it's just called seas. And so that's what you would get under this storm system in the picture here. In general, if that wind persists for a long enough distance, then waves generated under here will grow as they propagate under this storm in the direction of the wind. And the distance over which they grow is something called the wave fetch. Okay, so once they've been generated, the waves evolve through a couple of different mechanisms. One of which is that the steepest waves are liable to breaking. So they're too steep, the wind pushes the top over, they break and white cap. And this means the smallest wavelength and tallest waves get essentially removed from the spectrum of waves bumping around in the ocean, because they just break and fall out of the system and cause mixing, and they no longer exist in the wave field. The other way that the waves evolve is through interactions between multiple waves. So essentially the waves can superimpose, you can have multiple waves coming in, and so two waves come in and then two different waves can propagate out. And these are called nonlinear interactions. And on average, what these interactions do is move the waves to longer wavelengths and lower frequencies. So again, they sort of pull out the shorter scale and higher frequencies from the spectrum. And so if you look at a spectrum of waves, such as satellite observations, so here you've got what we call a probability density function of waves in frequency space. So the green here is showing you what they call a young wind sea, which is when the waves have first been generated. And you can see there's a lot of higher frequency energy. But as that wind sea matures and these interactions, nonlinear interactions occur and white capping and breaking occurs, it evolves into a lower frequency, mature wind sea that you can see in the orange. Now, of course, at some point, the wind event stops and you no longer are forcing the wave field, and then these interactions will cause all the very shortest waves and highest frequencies to essentially die out, and you're left primarily with the longer wavelengths. And these longer wavelengths that persist after the wind event are something we call the swell. And so these are quite stable because they're not going to be prone to these the breaking and nonlinear interactions, and so they tend to propagate over very, very long distances. And so these can propagate over many thousands of kilometers. So they might propagate all the way from the Southern Ocean to the coast of North America, for example, or across from the middle of the Tasman onto the New South Wales south coast. And these are the waves that arrive and provide the surfing conditions that all the surfers love so much. Now, as we already know from our previous calculations, the longer wavelengths of this swell will travel faster. So the longer waves will get ahead of the shorter waves and will arrive at the coast quicker.